Good evening, senior.
Good evening once again. Today we'll be starting with linear programming.
Good evening.
So the session overview. So we are saying linear programming is a mathematical tool that is used to analyze many real-world business problems. In this session, students are introduced to formulation of linear programming and the graphical approach to solving LPs of two variables. The LP is linear programming. All right. So the outline. At the end of the session, you must be able to model a problem, like the model formulation, graphical method of solving linear programming problems, convert linear programming models into standard forms, slack and surplus variables. All right. So I will like someone to read from this place. Mathematics review, linear algebra. Someone should read from this place. Someone should read it for me. Continue. Continue, please.
Most used words and their mathematical expressions must be, shall be, is, equal to, are all represented as with the equal to sign.
Okay, so
less when you are than or equal to.
When you are given a question like a word problem, and you find these words must be, shall be, is equal to, they are represented as what? The equal sign. Then less than or equal to, as the name depicts. You know how to draw the less than or equal to, that is the sign. At most, I've already taught you this. At most means less than or equal to. Must not exceed, not more than, are represented as what? Less than or equal to. So you must take note of this because you must keep this at your fingertips. Do you get it? We are going to use this one often. We are going to use them frequently. Greater than or equal to, as the name depicts. You know how to draw it. Greater than or equal to. At least, I've taught you that at least is represented as what? Greater than or equal to sign. Then between, if y is between x and z or x and z, it means what? Let's take a look at this. This is a straight line. We are saying that if y is between x and z, so x is here, z is here, right? Then we are saying that y is between them, between this x and y. All right, so we are saying that z is greater, this z is greater than x and is greater than or equal to x, and of course it's true. So the z here, which is this one, is greater than x, greater than or equal to x, because you will find z after what? X. And we're also saying that y will be less than greater than or equal to what? X, because we found the y here right after the what? X. So it means y is greater than or equal to x. And we are also saying that y is what? Less than or equal to what? Z. Of course, y comes before what? The z here. So if you hear something like if y is between x and z, z is greater than x, y is greater than x, y is less than or equal to what? Z. So z is greater than or equal to x, y is greater than or equal to x, y is less than or equal to what? Z. So any question up to this point? So these mathematical expressions are going to help you formulate your model. You are going to use these words: shall be, is equal to, must be. You represent that one as what? Equal to sign. Then must not exceed, has available to spend, not more than, at most, must not exceed, less than or equal to, represent it to what? Less than or equal to sign. Then greater than or equal to, at least, are represented as what? Greater than or equal to. This one is less than or equal to. This one is greater than or equal to. Then if something is between something, All right. If y is between x and z, it means y is in the middle of what? X and z. Then when it happens that way, z is greater than or equal to x. Y is greater than or equal to x. Then y is less than or equal to what? Z. And I illustrated this one on the number line here. All right. So, any question before we move on? Any question before we move on? Any question? Are we good? Can I move on? Okay, so here are examples. Number of products produced must not exceed 1,000. Now, we are saying that the X, which are the amount to be produced, must not exceed 1,000. Then it means the number of products to be produced must not exceed 1,000. So the X, which is the unknown product to produce, the number of products to produce, you don't know the amount, must be equal to or less than equal to, because we are saying it must not exceed something. When you are given 200 Ghana cedis and you are being told, oh, the money you have to spend must not exceed 100 Ghana cedis, it means you cannot spend more than the 100 cedis mentioned. So it's either you use the 100 cedis or you use what? Less than 100 cedis. That's why we represented X less than or equal to what? 1,000, because we are saying must not exceed what? 1,000. So you cannot use more than the 1,000. So either you use the 1,000 or you use what? Less than 1,000. And we are saying another point is what? X and Y must not exceed K. X and Y, and here means what? Summation, addition. You get it? You are adding them. All right. You are adding them, meaning when you add the two, it must not exceed K. So if you are told X and Y must not exceed 80, it should be X and Y plus Y must not exceed 80 to be like this. So when you add X and Y, it's either equal to 80 or less than 80. It cannot be more than what? 80. That's what the third point rule implies. Now let's move on to the next one. Pressure applied must be between 100 and 200 milliliters, right? Okay. So we don't know the amount of pressure in ml applied. Then let's represent that one with X here. You get it? So the X, it must be between what? 100 and 200. So 100 is here, 200 is here. So meaning that X, of which you don't know, should be here, in between of what? 100 and 200. So it means the X will be greater than or equal to what? Because the X comes after what? 100. So if X comes after 100, it means X is what? Greater than or equal to what? 100. It's either equal to 100 or what? Greater than 100, because it was after 100 that we found X. When it comes to 200, the X, of which you don't know, will be what? Less than or equal to 200. Because the X comes before the what? 200. Do you get it? Any question up to this point? All right, so let's continue. So the X is in between something. It means the X is greater than the 100 here and it's less than what? The 200 here. That's what it means. All right, so let's move on. Okay, so let's move on to the formulation. I'm going to introduce how you solve linear programming questions. Now, they are saying for you to be able to form a model like linear programming formulation, we have four main components in what? Linear programming formulation. So let me share that one on the whiteboard. All right, so we are saying that forming components in what? Linear programming formulation, right? So we have four main components in linear programming formulation. Before you formulate a linear programming model, you have to, okay, what is this? This okay, so the first one has to do with our decision variable. So you define your decision what? Variable, and I've taught you that one already. The second one, and I hope you know what decision variable is. Okay, so let me explain it for the sake of the first timers. Okay, so we are trying, all what we are trying to talk about decision variable is what? The item or the product in question. So that's the decision to be what? Made. And you are not interested in the product or the item itself. Let's say you entered the phone shop and you're having 6K in your hands. Cash in hand is 6,000. And you are planning to buy either Techno, Samsung, you get it. But you don't know which or how many phones or how many products you want to buy, you get it. But you know that type of product you are going to buy. So let's say you enter the mall with a certain amount. So you're having this sum of money, let's say 1,000 Ghana cedis. You are planning to buy provisions for yourself. You get it. You know you buy Milo milk and stuff, but you don't know the quantity to buy. So you represent that unknown quantity with the X1, S2, S3, and that's what we termed as our decision variable. We are only interested in their quantity. You get it. We are not interested in their in the item itself. We are interested in the quantity. So the quantity, unknown quantity, we represent that one with what? S1, S2, S3. That's why we term as decision variable. And I hope by this time all of you know this one. So let's move on. The second one is what? Know your objective function. Objective function. Now, another objective function is either we are talking about our profit or cost. And from business mathematics, relative extrema, every rational entrepreneur wants to what? Maximize his or her profit. You get it? And every rational entrepreneur want to what? Minimize his or her cost. You get it? So it's either we maximize profits, or we minimize what? Costs. And there's this third one. They are saying it's customer satisfaction. But for me, I will not add that one. All right. So decision variable, first of all, you define your decision variable. You what? Find your objective function. So if it is cost, you just find the objective function. You come to that, you understand more about it. If it is cost, you find your minimization cost, maximization profit. So how do you maximize your profit? How many products to produce? How many products to produce in order to attain your highest profit? The minimize cost to like something like that. That you want to minimize your cost. You want to get the least cost. So how many products are you going to buy? How many products are you going to sell to minimize your cost, to get the least cost? You get me? The third one has to do with what? Resource constraints. Resource constraints, or the constraints. You get me? The resource constraints. So that one we have land, labor, budget, capital, material, and the rest. You get it? And the fourth one, we have something like non-negativity constraints. Non-negativity constraints. So with the non-negativity constraints, it means all your decision variable value or all your decision variable cannot be negative in the production sector. Now, I hope you've not heard of producing something negative in the production sector. You are producing this sachet water, and you are being told, oh, today we produced negative 20 of sachet water, or we produced negative 20 bags of cement. No, in production, you don't have negative production. We don't have negative number in the production sector in terms of production. So with the non-negativity constraints, it means all the decision variables cannot be negative. In other words, all the decision variables are greater than or equal to at 0. So in production sector, it's either we don't produce nothing at all, we produce nothing at all, like we produce 0, or we produce what? More than 0. We don't produce negative number less than 0. No, that's why we term it as what? Negative number, negative non-negativity constraints. So that one has to do with what? Representing your decision variable. So if you have x1, x2, s3, let's say xn, then that one will be what? Greater than or equal to what? Greater than or equal to what? 0. So that's why we term that as what? Non-negativity constraint. So before you'll be able to solve linear programming question, you go through all these 4 steps. So after getting your variable, objective function, resource constraints, non-negativity constraints, then you move on to what? The graphic method, because we are going to, first of all, we are going to learn how to use the graphic method to solve for the decision variables under the linear programming. And also after that, I'm going to teach you how to use Microsoft Excel to solve all these things. You get it? So any question before I move on? Any question under the components in linear programming formulation before I move on? Any question at all? Like any question? Because I'm going to pick a question straight away, then we solve. So if you have a question, let me know before I move on. Any question? Okay, so Bastios is saying, no, why is this thing happening like this? Can you see the writings, like the question I've posted? Can you see it? Can you see the question here? Yeah. I'm seeing something different at my end. All right, let's continue. So, okay. So this is a typical question. Okay, let me clean this one. So the first one, a linear program is a mathematical optimization model that is made up of what? A linear objective function and a set of what? Linear constraints. I think I've already explained this. So let's move on to what? Example number 1. All right. So someone should read it for me. Someone should read it for me.
Yeah, it will recover. It manufactures 2 types of food twice. So just instruments. So just cells for 3 cities and train cells for 2 cities. Manufacture of food and soldiers and trains requires 2.
Please, who is reading? I cannot hear the person. Someone was reading, but I can't hear the person.
toys. Soldiers. A soldier sells for 3 cedis and a train sells for 2 cedis. The manufacture of wooden soldiers and trains requires 2 types of skilled labor, carpentry and finishing. A soldier requires 2 hours of finishing labor and 1 hour of carpentry labor. A train requires 1 hour of finishing and 1 hour of carpentry labor. Each week, Gyapeto can obtain all the needed raw materials, but only 100 finishing hours and 60 carpentry hours. If at most 40 soldiers are bought each week, and Gyapeto wants to maximize weekly profit, formulate a mathematical model of Gyapeto's solution that can be used to maximize Gyapeto's weekly profit.
Okay, so thank you, Tina. First of all, how many decision variables are in this question? They are saying that Gyapeto's Wooden Carving Incorporation manufactures 2 types of wooden toys. So how many decision variables?
2.
2, okay. They are. So the 2 includes the wooden toys. You get it? Because they are saying that incorporation manufactures 2 types of wooden toys. You get me? So the first one, they are saying that the first one is what? Soldiers train toys. Soldiers toys. And the second one is what? Trains toys. You get it? So the decision variables are 2. So soldiers toy and what? Train toys. And I said it that the decision variable is not interested in the item or the product itself. We are in under decision variable, we are interested in what? Their quantity, their unit, the amount of, you get me, the number of. So by the definition, we define it as, so first of all, we are defining our what? Define your decision variables. So first of all, we are saying let x1 represents the, because number of, yes, we are interested in their number, not the item itself. Number of soldier toys to produce. You get it? Because the question is asking, formulate a mathematical model of Gyapeto's situation that can be used to maximize Gyapeto's weekly profit. So how many products, how many soldiers toys can we produce in a week? How many train toys can we produce in a week to maximize Gyapeto's what? Profit in the week? So we don't know the quantity. So we just represent the quantity with what? X1 and S2. So the first one represent that one is what? S2 to produce in a week. You get it? Then let X2 represents the number of what? Trains toys to produce in what? A week or per week. All right. So we've done the first one here, decision variable. Now we are moving on to what? The objective function. Who can tell me the objective function here? Who can tell me the objective function? I just explained the objective function. I said the objective function is either we maximize our profit or we minimize our cost. We know this from relative schema, business mathematics last semester. Right? So what is the objective function here? What is the objective function here? Oh.
To maximize profit.
Good. So we are talking about the maximize. So maximize. Yeah, let's represent that one with Z. So maximize what? Z. We don't know the So that one we are going to formulate it. So we are saying that how do you know your objective function? Profit. So when you read this part, you are saying that a soldier sells for what? 3 Ghana cedis. And a train sells for what? 2 Ghana cedis. So we are going to use their unit price as what? Their unit selling price as the objective function. So the unit price for soldier is what? 3. And what was the decision variable for soldier's toy? What was the decision variable for soldier's toy?
X1.
X1. All right, thank you. So X1 plus X1 plus the selling price of what? Train toys. Like, I mean, one unit, because we are saying a means one. A train sells for 2 Ghana cedis. So we are going to use the unit selling price. You get it? So the unit selling price for train toys is what? 2. You get it? And what is the decision variable for train toys? What is the decision variable for train toys?
X2.
X2. All right, thank you. So S2. So this will be your objective function. You get it? This is going to be your objective function. So first of all, you define the decision variables. You move on to your objective function. Thirdly, you are going to formulate what? Resource constraints or the constraints. When you read through the question, we are saying that the manufacture of wooden soldiers and train toys requires 2 types of skilled labor. Now, if you require something, it means that one becomes your what? Resources. Because without that resources, you cannot what? Operate. Because they are saying they require 2 types of skilled labor, carpentry and finishing. If they don't have the carpentry department, the finishing department, they cannot what? Sell what they want to produce. You get it? So that becomes our resource. So the finishing and the carpentry, our resources or the constraints here. You get it? So we move on to the third one, which is the constraints. You get it? This is the constraint. Now we move on to the constraints number 1. So we tackle the finishing first. Finishing. So the finishing, they are saying that a soldier requires 2 hours of finishing labor and 1 hour of carpentry labor. So a soldier requires 2 hours of what? Finishing labor and 1 hour of what? Carpentry labor. A train requires 1 hour of what? Finish. So when you take the soldier, you are going to see finishing labor, the hours needed for finishing labor, the hours needed for what? Carpentry labor. When you take train toys, you are going to see the hours needed for what? Finishing labor, hours needed for what? Carpentry labor. And when you read through here, you are going to see their what? Their available resources. We are saying that the Gepito can obtain all the needed raw materials, but only 100 finishing hours and what? 80 carpentry hours. That becomes our available resources. So you formulate your model, you use the less than or equal to, then you bring your what? Available resources. So when you talk about the finishing, the available resources becomes the 100 here. You get it? All right. When you talk about carpentry hours, we are going to use the 80 here. All right. Okay. So the constraint, I said we have two constraints. Oh, by the end of the question, we will have 3. But let's focus on these 2, finishing and carpentry, because they are saying that the wooden Jopito's wooden carving wood carving competition, manufactures 2 types of toys, and they require 2 types of what? Skilled labor. That is this carpentry and finishing. So when you talk about the finishing, right? You are saying that, where is it? A soldier. So let's pick that one of the soldiers. So a soldier requires 2 hours of what? Finishing labor. So we are dealing with finishing. So when you talk about soldier, it requires 2 hours. 2. What are the decision variables? So 2 hours times the number of toys, soldier toys to what produce. We don't know that number. We represent that one with what? X1. You get it? Plus, we move on to search for the finishing hour for what? Train toys. When we read this part too, you see that a train requires 1 hour of finishing labor. So we have 1. The variable is S2. 1 S2. Don't write 1 S2, it is X2. All right. Then the available resources was what? Each week, Giapito can obtain all the needed raw materials, but only 100 finishing hours. So, but only 100 finishing hours. Now, if you hear the words, but only, which sign are you going to use? But only. Who can tell me the sign you are going to use? Who can tell me but only? Oh. Who can tell me? So here you are going to use what? Less than or what? Equal to. But only you use less than or equal to. Less than or equal to. But only you use less than or what? Equal to. All right. So any question before I move on to the next constraint? The next constraint will be carpentry. So any question before I move on? Any question before I move on? Hello. Well, I guess you understood it. All right. So we are going to talk about what? The carpentry. So we are going to use the number of hours needed for carpentry when we are going to what? Manufacture a soldier toy. We are saying that a soldier requires 2 hours of finishing, we've dealt with that, and 1 hour of what? Carpentry labor. So when you are producing a soldier toy, you require 1 hour of what? Carpentry. Do you get it? So the X1 will be 1. So it will be 1 here. 1 here. Then plus, move on to read a train requires 1 hour of finishing. 1 hour of what? Carpentry labor. So when you are manufacturing train toy, you are going to need, you require 1 hour of what? Carpentry labor. So the finishing labor, the carpentry labor for soldiers, manufacturing soldiers toy is what? 1 hour per a product. You get it? Then when you are manufacturing the train toy, that one to require you what? 1 hour of what? Carpentry labor. So that one to 1s2. 1s2 is the same as what? X2. You are having but only what? 80 carpentry hours. 80 carpentry hours. 80 carpentry hours. So, but only you are going to use less than or equal to what? 80. All right. So, any question before I move on? Any question? This should be our constraint, but when we read through the question, if at most 40 soldiers are bought each week, and Jopetos want to what? Maximize weekly profits. So if at most, what is the sign for at most? Who can tell me the sign for at most?
Less than or equal to.
Less than or equal to. All right, all right, all right, all right. All right. So we are saying that if at most 40 soldiers are bought each week, 40 soldiers are bought each week. So the decision variable for soldiers was x1. So x1. At most, we are saying that it's less than or equal to what? We are saying if at most 40 soldiers, so less than or equal to what? 40. So this will be your what? The constraint. The constraint. So this will be our constraint. So this one was what? Demand was. Let's name this one demand. Okay. Let's name this one demand. So we are done with our constraints. Now the next one we are going to deal with is what? Non-negativity constraints. Because this one is production, you are manufacturing something. Non-negativity constraints. You get it? And we are saying that in terms of production, we don't have a negative number. You cannot produce negative. You either produce 0 or you produce what? More than 0. So you produce nothing at all, or you produce what? More than 0. Do you get it? So that one, you represent your decision variables. You write your decision variables to what? Greater than or equal to 0, because it cannot be less than 0. So this one, decision variables are 2. You can write x1 greater than or equal to 0. S2 is greater than or equal to 0. Or you can write x1 comma S2 comma greater than or equal to 0. So this is how our non-negativity constraints are going to look like. Now from here, we are going to use the graphical method. And I taught you that one in the previous meeting, in the previous video, graphical approach to solve for what? To solve for x1 and x2, right? You get it? So let's talk about what? Let's develop coordinates for the finishing. So coordinate for finishing. Now we are saying when s1 is 0, hold on for me, I'm coming. Let's continue. Sorry for the. All right, so when s1 is 0, what will be the value for s2? S2 will be equal to what? S will be equal to what? Oh, you've done this calculation. Please do it for me. So if x1 is 0, s2 will be 100. So the coordinate will be 0, 100. Then the same expression, you represent S2 with 0. So when X2 is 0, you represent X1 with what? When X2 is 0, what will be the value of what? X1. So X1 will be at 50. The coordinate will be 50, 0. So this is the coordinate for what? Finishing. Let's move on to what? Carpentry. So the carpentry to the expression when X1 is equal to 0, X2 will be 80. Then it will be 0 what? 80. Then the same expression, you make S2 to be 0. So when S2 is 0, X1 is what? So when S2 is 0, X1 is 80. So that onto the coordinate will be what? 80, 0, because S1 comes before S2. Now let's move on to the demand expression. Demand. So we are saying the demand to, this one is only one, right? So when X1 is 40, S2 is what? 0. We don't have any S2 here. So the coordinate will be what? 40, 0. All right. So now that we've derived, so this is how we derive coordinate from an expression, right? I've done this several times, so I'm not going to waste time here. Right. So we are moving on to draw the graph. Now, let's draw the graph. So this side is 0. This one is our S21. So let's use 10, 10, 10, 10, right? So 10 here, 20. Am I recording this? Okay. 30, 40, 50, 60, 70, 80, 90, then 100. Let's do same for X. Oh, this one is X1, sorry. Then this one will be for S2. So 10, 20, 30, 40, 50, 60, 70. All right, so I think this is okay. So let's draw that of, let's plot that of finishing. So the finishing, the first one is 0, 100. So when, let's use 0 for this one, yellow. So when X1 is 0, X1 is this one, S2 is 100, so it will be here. The second coordinate is what? When X1 is 50, S2 is 0. So X1, S2 is 0, X1 is 50, so it will be here. Join that one. join these points. So this one will be what? The straight line will be the equal sign. So 2x1 plus x2 equal to 100. Every straight line on the straight line is the equal sign, but the shaded area will be what? The less than or equal to. So this one is less than or equal to. So we shade what? Downward. So we shade like this. I've taught you this in the previous video. So shade to cut the x1 and s2 what? Axis, or x and y axis. All right. So the shaded area here becomes your less than or what? You're equal to. So that one will be 2x1. I'm just illustrating this one. I will not write the rest. S2 less than or equal to what? 100. You get it? Okay, so we are done with the finishing. So this the line for the what? Finishing. So let's move on to the carpentry. Carpentry, let's change the color. Let's change it to pink. Okay. So when x1 is 0, so when x1 here is 0, s2 is 80, so it will be on the s2 axis. So here. Then when s2 is 0, s1 is 80. When s2 is 0, x1 is 80. When s2 is 0, so it will be here on the s2 axis. That one to you join the point, join the two of them. So that this one too is less than or what? Equal to. So you shade downwards. You are going to shade downwards. So the pink line you are going to shade. I didn't want that one to be confusing. That's why I'm using different colors. But in exams or something like that, I'm not going to get time for this color or something like that. So just observe it. So it should be on the straight line coming downwards. You get it? I mean the pink, the second line. Cool. So let's draw that one for the demand. Demand, we are saying that let's use different color. This time around, I'm going for black. No, I'll use black for sure. Okay, black. So when S1 is 40, S2 is 0, so it will be here. So this one is going to be a straight line upwards. You are going to draw it from here, going top. This one is what? This one is less than or equal to, so that one to shaded area coming down. Why is it too easy? Hey. Must shade to cut the S2 and what? So now, oh, it shouldn't be beyond the line. Yes, so this, something like this. Okay, it's okay. So we are going to shade like the feasible region. And remember I told you in the previous video that the feasible region or the feasible area is where we are going to find your optimal solution. Because any point in the shaded region, okay, you let me shade the feasible one. So let me use green. So that one, you are going to shade wherever you will see the three colors, wherever you are going to see yellow, pink, and black, you're going to see shade that place. So it starts from this place, coming downwards to where the 0 is. You see the all the three colors, right? You see yellow, pink, and black. Then move on like this, like this. When you end on the black, that's the 40. Here you only see what? Yellow and pink. You don't see black, so it ends here. It moves up like this. You get it? Then you shade on the yellow line, because above the yellow line, you are going to see only what? Black and what? Black and pink. So it will be on this line, yellow line here. You get it? And this part. Then you shade the area of, you shade this area. So the green line will be your border line, right? So I may not get time to shade it because it's not easy to do it with the mouse. So the green line is the border line. Let's take it like that. Now we are going to pick some points here. So those points will be our so any point in the shaded region is a feasible solution, but not necessarily an optimal solution. I taught you what an optimal solution is. Optimal solution is the exact value for x1 and x2. So using the equality, you draw the two lines. That one you are not going to shade. So wherever they meet becomes your what? Optimal solution. But this one, it is what? Inequality. So we shade. And we don't know the optimal solution. This one is maximize. So we don't know the highest values. You get it? So we are going to pick the point. So the shaded area touches this point 0, 0. It touches here 40, 0. Another one too is this side. It's a point, right? Then one is here. The last one is where? At this side. So let's name this side A. Let's name this side B. Let's name this side C. Let's name this side D. Then let's name this point G. Now picking the point, picking the point with the A, picking the coordinate with the A is what? 0, 0. With the B is what? Who can tell me the point for B? The point for B is what? The S1 is 40. S2 is what? 0. So 40, 0. C. This is C. So who can tell me the value for C? So this one is not drawn to scale. So unless I tell you here. So this one, the X1 was what? 40. You get it? 40, and S2, when you trace it to this side, it should be 20. But this one is not drawn to scale. So it's what? 40, 20. The point for D is what? Who can tell me D? D is clear. It's on the 80. So what will be the D? D is 80, 0, 80. Then Y is what? This one is 20, S2 is 20, but it is not drawn to scale. That's why I'm telling the values. So this one is 20 and what? 60. 20, 60. So now that you've picked the corner point of the shaded region, you are going to pick each one of them. You get it? And test it. So the one that yields the maximum point or the maximum Z, it becomes your answer. So which function are you going to use? Remember, we formulate, we got this one, objective function, maximize z as x1 plus x2. So you are going to use this function. So x1 will be the first values after the commas. That one too becomes our s2s. Then you substitute it into this function. So when you pick A, you substitute it into A. Pick B, so s1 will be here, s2 will be here. Then you substitute it into the function. So after your answer, the highest value becomes your answer. So the highest value becomes your answer, and the coordinate will be used to determine the answer for what? S1, S2, and what? S3. So are you clear with it before I move on? All right, so the objective function is what? So the objective function is what? 3x1 plus 2x2. You get it? So when you pick the first one, 3x1, what is the x1 for point A? Point A, the x1 is what? 0 plus what? 2x2. We are using this function. So 2x2, the s2 is 0. So here everything will be 0. So here you are going to get 0 for this part. B, 3s2. S1 is what? 40 plus 2x2. x2 is 0. So this one will be what? 120 plus 0. So it will be 120. So the B point will be 120. Let's tackle with the C. C, yes. So the C is 3x1. What is the x1 for C? 40 plus 2x2. x2, what is the value of what? 20. s2 for C is 20. So this one, by calculation, this one will give us 120 plus what? 40, which is going to give us what? 160. Then the D, 3x1. So what is the x1 value for D? It is 0 plus 2s2. s2 is what? 80, right? So this one will be 3 times 0 will be 0. 2 times 80, 160. So the D2, you get your value becomes what? 160. Then move on to E. So 3x1, what is the value for x1? Is 20 plus 2x2. What is the value of x2? Is what? 60. So by calculation, you get what? 180. 180. So the E2 becomes our what? 180. Now, your final answer depends on the question. The question was telling us to what? Find or formulate a mathematical model of the situation that can be used to maximize. So here the question is talking about maximize. Do you get it? The question was talking about maximize. And if it is maximize, then it means you are going to pick your highest value. So what is your highest value in this? What was the highest value? What was your highest value?
180. 180.
Good. Therefore, so your 180 becomes your optimal solution. So therefore, the value here, so this one becomes our what? X1, 180 is point E. Then the 60 becomes what? X2. So meaning the actual value for our x1 and s2 that was unknown is 20 and 60 respectively. Therefore, Geopetus or Geopetus would have an incorporation. And to manufacture or produce 20 soldier toys and 60 train toys to obtain a maximum profit of what? 180 Ghana cedis, and that will be your answer. I repeat, the 20 here becomes your answer for what? X1. 60 here becomes your answer for S2. So you write, therefore, so let me write. Therefore, Geopetus should produce 20 soldier toys and what? 60 train toys to obtain maximum, because we are talking about maximized profit, maximum profit of what? 180 Ghana cedis weekly or per week. That one becomes your final answer. So this is how we used the graphic methods to solve for the inequality aspect. So any question up to this point? Okay, as I told you, the feasible region and optimal solution. So the feasible region for an LP is the set of all points that satisfy all the LP's constraints and sign restrictions. You get it? For a maximization problem, an optimal solution to an LP is a point in the feasible region with the largest objective function value. So when you get a maximization problem, so the problem you solve, the operators within incorporation, that problem was related to what? A maximization problem. So that one, we are going to find the largest objective function value. That's why after substituting this thing, the coordinates or the corner point into the objective function, after everything, we picked the highest one. That was what? Point E. And the coordinates were 20, 60. The objective function, the largest objective function value we got was what? 180. So that one becomes our answer. Opposite, similarly for a minimization problem, that's when we are talking about cost. So the moment you see maximization, cast your mind on what? Profit or revenue. When you see minimization problem, it's talking about cost. So when you get a cost problem, an optimal solution is a point in the feasible solution with the what? Feasible region with the smallest objective function value. You get it? So similarly for a minimization problem, an optimal solution is a point in the feasible region with the smallest objective function value. All right, so that's what they are trying to tell us. And basically this one, I've illustrated it on the white sheet to you. We drew the graph, plotted everything. I explained everything to you. So you just read this note for, so this is the graph I drew, you see. So we have an A, B, C, D, G. So here the point was G. So the G becomes our final answer. So you are saying any point in the shaded region is a feasible solution, but not necessarily an optimal solution. The optimal solution will be one of the corner points. So the optimal solution will be one of these, this one, this one, this one, and this. One of this one, this E here, F here, and G. So one of the alphabets can be our optimal solution. And by working, we got the answer to what? 180. The 180 becomes our answer. So X1 was 20, S2 was 160. We picked the Z, that's the maximization, the maximize Z, and we substituted S1 and S2 into this function. we got the answers to be this. Do you get it? Good. So you pick the highest one because this one was a maximization problem. If it is a minimization problem or cost, you pick the lowest one. It should have been what? It will be 120. Should have been this 120. But this one is talking about maximization rather. So we are going to choose the highest value. So that one becomes the 180. Now, using this method, we are having alternative method there. That one they call it ISO profit line. They are saying alternatively look for the lines that intersect to generate the optimal point and solve for them. You see these dotted lines, that's what they call the ISO profit line. But this point is simple. What I taught you is simple for me, yes, and I will recommend that one to you. So I won't bother to teach you the dotted one. That dotted one, you draw a dotted line farther from what? The zero or the origination. You get it? So it touches the last shaded point. I will not teach you this one. I don't want that one to confuse with what I just taught you. So what I taught you is the simplest form. You get it? By picking the point that touches or the feasible regions, like the corner points. The corner point was 1, 2, 3, 4, and 5. The boundaries of the shaded region, they are points. You pick them. You get it? You write all of them down. You write your objective function here. You substitute your corner point into the objective function. You get certain values. If it is maximization, you pick the highest one, that becomes your answer. If it is minimization cost, you pick the lowest one, that becomes your answer. So I'll not bother to teach you the so-called ISO profit line. All right, so let's move on. So basically, so move ISO profit line. So they are telling us more about what we solved. Okay, so now we move on to binding and non-binding constraints. So this part is also very, very important. So we are saying a resource or a constraint is binding if the left-hand side is and the right-hand side of the constraint are equal. In other words, if LHS, left-hand side, is equal to what? RHS, right-hand side. So after getting your values, now, let me write this one down. The objective function for finishing was what? The expression for finishing was 2x1 plus what? x2 less than or equal to what? 100, right? And we are saying after getting your answers, you are going to check whether the constraints were binding or not. Do you get it? So we are going to substitute the value of x1 and s2 into the finishing. All right, so the value of x1 and s2, you substitute it into this expression. So the value of x1 was what? 20 plus value of s2 was at 60 per what we did, less than or equal to what? 100. You get it? So this one, 2 times 20 will give us what? 40 plus 60. It should be less than or equal to what? 100. And exactly that's the answer. 100 is equal to or less than what? 100. So it means this constraint, the finishing here, was binding or is binding because all the resources were used. So we are saying that a resource is said to be binding if all the resources allocated have been fully utilized. So a resources or a constraint is said to be what? Binding if all the resources allocated to it have been what? Fully utilized. Let's check the carpentry one. The carpentry one, it was what? x1 plus s2 less than or equal to what? 80. And what was the value of x1 and s2 after our answer? After our calculation, it was 20, S2 was 60, so plus 60. We are getting what? 80 less than or equal to what? 80. It means the carpentry constraint 2 is what? Binding, because all the resources, all the number of hours allocated to carpentry, because the number of hours allocated to carpentry in a week was what? 80. So all of them were fully utilized. And we using now, they were utilized. So that one is binding. Now let's check that of demand. Demand was what? X1 is less than or equal to what? 40. S1 was what? 20. So when you look at this, it's less than 40, but it's not equal to what? 40. So this means the demand constraint was not what? Binding, or it's not binding, because the left-hand side is not equal to what? The right-hand side. You get it? So it was not fully utilized. They didn't use all the resources, or resources allocated to it. The thing was 40, but at the end of the day, we got 20. You get it? They demanded 40, but at the end of the day, we produced 20 per our calculation. You get it? So the X1, which is the demand constraint, was not binding. So in simple words, a resource is said to be binding if all the resources allocated have been fully utilized. So that's the binding and non-binding constraints. All right, so let's move on. Any question before I move on? Any question before I move on? All right, we have something like LP in standard form. Now, LP in standard form, we are saying when all resources constraints are in equality form, the LP problem is said to what? In a standard form. To express an LP, it's linear programming with inequality resource constraints into standard form, slack variables for less than or equal to constraint and surplus variables for greater than or equal to constraint are employed. Now you see that our questions, we use what? Less than or equal to, less than or equal to. So it's not in the standard form. So the standard form helps us to what? Change this less than here to our equal sign. So how are you going to do that? If you get less than or equal to, it means you are going to introduce what? A slack variables. So the slack variables is what? The unused resources. Resources now when you use, that's the slack variables. And the surplus, as the name depicts, over like the excess. So if you didn't use something and you want to add up to make it equal to your available ones, you just add your unused resources. When it is about excess or surplus, you just subtract it from what you used. That's what they are trying to tell us. So the slack and surplus something is not that important, but you should understand that one. So you see this one, it was 2x1 plus x1, because our formulation, we got this 2x1 plus x2 less than or equal to what? 100, right? But the standard form is saying that we should make everything equal. So if we should make everything equal, then we must introduce our slack, the unused one. So the unused one, let's represent it with what? S for small, right? So plus S2 plus X is equal to what? 100, right? That's 100. So that becomes your slack value. So you work for it. So the slack and the surplus, like I don't know how to put it. You don't have effect on your expression. No. You get it? So this one to x1 plus s2 was less than or equal to at 80. The carpentry one. Then there's to introduce the slag. The slag is the unused, so we must add plus S2. Then equal to what? 80. Then you solve for your slag variable. Do you get it? So the same applies to the last one. X1 plus what? S3. Is equal to what? 40. 40. You get it? So S1 plus S3 equate it to what? 40. So the slag is just bringing the unused one. The surplus is subtracting the excess one. All right. Let's make progress. All right. So the slag variables, as I said, standard form requires that all constraints be in the form of equations or equalities. So the standard form requires all constraints to be formed in the form of what? Equations. So a slag variable is added to what? A less than or equal to constraint or weak inequality to convert it to an equation. So as I said, you bring what? Slag variable when you have what? A less than or equal to. That's a weak inequality. To make it what? Equal. A slag variable typically represents an unused resource, as I told you earlier. A slag variable contributes nothing to the objective function variable. That's what I was trying to tell you. The slag, when you introduce a slag variable, it contributes nothing to the objective function. The objective function, the maximize, this slag variable contributes nothing to it at all, because this one was part of the constraint, just that it was unused. So it does nothing to our objective function. All right. So the same thing applies to it, the surplus. Let me move on to the surplus. So the surplus is the opposite of what? The slag. You introduce the slag whenever you have what? A strong constraint, a strong inequality. So a surplus variable is subtracted from what? A greater than or equal to constraint to convert it to what? An equal equation. Which is equal sign. A surplus variable represents an excess above a constraint requirement level. Surplus variables contribute nothing to the calculated value of the objective function. So the same thing as the slag, it contributes nothing to what? The objective function. So subtracting slag variables in the farmer problem constraint. So you add slags to your constraints. You subtract surplus from your constraints. I repeat myself. You add slags to your constraint. You subtract surplus for your what? From your constraint. Okay, so the question we solved was about what? Maximization. The question we solved was what? Maximization. This one, this question, the Giapito's one was what? A maximization. Now let's move on to solve what? A minimization or cost question. So this is our cost question here. So someone should read it. Let's continue.
Two brands of fertilizer available, Super Grow and Crop Quick. Field requires at least 16 pounds of nitrogen and 24 pounds of phosphate. Super Grow costs $6 per bag. Crop Quick, $3 per bag. Problem: how much of each brand to purchase to minimize total cost of fertilizer given following data? Chemical contribution, brand, nitrogen, LB/bag, phosphate, LB/bag, Super Grow, nitrogen, 2, Super Grow phosphate, 4, crop quick, nitrogen 4, phosphate, crop quick, phosphate 3.
Okay, so with this one, they've done the constraint for us, simple. So first of all, thank you, Boss. So first of all, we are saying that to formulate this kind of problem, you have to go through the 4 main components. So first of all, we define our decision variables, right? So let's define our decision variables. Now, how many decision variables do we have here? So here we are having 2 decision variables. You get it? So first of all, let's x1 represents, okay? I'm coming. Let x1 represent bags of what? Super glue, right? Bags of super glue. So, can you see the white screen?
Yes, I can see the white screen.
Represent bags of what? Super glue. Let S2 represents bags of what? Quick pro. Is it pro or what? Yes. So we are done with what the definition of what? So definition of the decision variable. We've defined our decision variables. We also talked about the second one is what? The objective function. Now the objective function, I said we have either maximize cost or maximize profit or minimize cost, right? So in this type of question, it was a cost question. So we are going to minimize cost. So minimize z, you get it? Minimize z is equal to let me share this, right? So they said the super glue cost. So this one, the unit cost. So the super glue cost $6 per bag. So $6 per bag. So $6 per bag. So $6 per bag of what? Super glue. We don't know the quantity. So the 6, the unit cost. The quantity we represented that one at what? X1 plus what is the cost value, unit cost of crop quick. That one is $3 per bag. So that one will be 3S2. So this one will be what? 3x2. So this one will become our what? Objective function. Now let's move on to what? Our decision constraints. The constraint. First of all, we have what? This one, they've done it for us here. We have super glue, we have nitrogen and phosphate. Those two are our constraints, and the available resources for them are 16 for nitrogen and 24 for what? Phosphate. So the super glue, we have 2. You get it? So 2x1 plus the crop quick and the nitrogen, you have 4. So 2x1 plus 4s2 less than or equal to what? 16 pounds of nitrogen. So that will be, let me write that one here. So super. So nitrogen. 2x1 plus 4x2. This one is at least. They are talking about at least. I said at least is what? Greater than or equal to what? That
equal to.
All right. So greater than or equal to 16, right? Then let's move on to the phosphate. Phosphate. So that one too, they said it is 4 relating to super glue, 3 relating to crop quick, and the available resource was 24. So 4x1 plus 3s2. So 4x1 plus 3x2. All of them are at least, so greater than or equal to 24. So these are our constraints. Now let's move on to our non-negativity what? Non-negativity constraints. And I said that one is the easiest among all, right? Just represent your decision variables greater than or equal to 2. So this one we have only x1 and s2. So s1, s2, s1, s2, greater than or equal to at 0. So now that we are done, we are going to develop the coordinate from the constraints. So under nitrogen, when x1 is 0, s2 becomes, so x2 becomes, so 2x1, we say that let's represent x1 with 0. So 2x1 0 plus 4s2 greater than or equal to 16. Okay, so this one will be 0. So it will be left to at 4x2 greater than or equal to at 16. So you divide both sides by 4. You are getting what? S2 to be greater than or equal to at 4. This is how we do the workings. All right.
Okay.
So S2 will be what? 4. So the point will be x1 comes first, 0, then you bring your S2, 4. The same thing, the same constraint, you make S2 to be 0. So when x2 is 0, what to be the value of x1? Right? So the whole of this will be 0. So it will be left with 2x1 greater than or equal to 16. So you divide both sides by 2. So your x1 will be what? 8. You get it? Good. So your point will be 8, 0. So this will be a coordinate for nitrogen. Let's move on to the phosphate. So phosphate, when x1 is 0, x2 is what? S2 is, so let me do that one here. So when x1 is 0, so 4 times 0 plus 3s2 greater than or equal to what? 24. So this one will be 0. So you just divide both sides by 3, right? Because you want to know the value of s2. 8. So x2 will be what? Greater than or equal to 8. So s2 will be 8 in the what? Coordinate. So s2 will be what? 8, right? So the points. So the point will be 0, 8. When x2 is equal to 0, what will be the value of what? X1. So 4x1. So 4x1 will be 0. So to be left with what? 3s2. Oh no, sorry. So the s will be 0. So the whole of this one will be 0. So it will be 4x1 greater than or equal to what? 24. So you divide both sides by 4, here by 4. So this one will be x1 greater than or equal to what? 24 divided by 4 will be what? 6, right?
6.
All right. So 6. So the point will be what? 6, 0. So you just plot the graph. So this one, let's do it 2, 2. The interval, let's do it 2, 2. 2, slow, 4, 6, 8. So this one is what? X1. 2, 4, 6, 8. Okay. So let's plot them. So when x1 is 0, s2 is 4. When s1 is 0, s2 is 4. It will be here. Let me change the color. Do you get it? Then when x1 is 8, s2 is 0. So it will be here. Join them. Right? So this one is less than or equal to. So you are going to shade what? Upwards. You are not going to shade downwards. This one is greater than or equal to. So shade upwards. All right. Okay. So let's move on to what? The phosphate. The phosphate 2, it is what? When x1 is 0, s2 is 8, it will be this one. When s2 is 0, x1 is 6, so here. You join the 2 points. This one too is greater than or equal to, so shade upwards. So this one is quite different from what? The maximization. The maximization, you shade downwards, but this one is what? Minimization. So you shade what? Upwards. You get it? So this one, when you look through it carefully, it is from this side, the orange line. So if you are to shade, to be on this line, to be on this line, this green line here, this orange line, then red line here, and shade here, and this side to here, all this place. You get it? So this one is quite different. So this one you are going to get how many points? The same thing we did for the other one. I'm going to get 1 point here, the second point here, and the third point here. You are getting 3 points. So the first one will be 5 something. So you are going to develop the point. This one is what? Minimize. We are going to derive the point. So A is what? 0 and 8. So let's name here A, B, then C. So this one is what? 0, x1 is 0, s2 is 8. So with the A, we are having what? 0, 8, right? B is not drawn to scale, so it will be quite difficult. So let's say you go for 5 and 2 or something like that. Yes, the S1 is 5, S2 is what? 2. Then the C, maybe what you see will be different from mine because it's not drawn to scale, right? So the C2 will be what? 8, 0, 8, 0. And this one, our objective function was what? What was the objective function? 6x1. It was minimized, 6x1. So minimize z is equal to what? 6x1 x1 plus 3s2. Okay, thank you. 3s2. You get it. So you have all these values. The first value is the one before the comma and for x1, the one after the comma and for s2. So you are going to pick the first one is 0, 8. So 6x, let me reduce the list. So 0, 6, 0 plus 3, s2 was what? 8. So what will be the answer? 24, right? So the point A, the value is what? 24. Let's work for that of B. 6, x1 is 5 plus 3, s2, it is 2. So this one 30 plus 10, you are getting what? 30 plus 6, you are getting 36. So this one too is 36. Let's do that of C. 6 times 8 plus 3 times what? 0. You are getting what? 6 by 8. 6 by 8. You are getting 48. Plus what? 0. This one is not a maximization question, or this one is not a profit question. This one is cost. And I said it that every rational entrepreneur or a businessman will go for what? Like the minimum cost. You get it? So here, the answer for x1 and x2 are the least one is what? 24, right? So the S1 is 0, S2 is 8. So the X1 is 0 and what? 8 respectively. And the cost is what? The minimum cost is what? 24. Minimum cost is what? 24. So this is the opposite of what we did earlier. So any question? Any question?
Yeah, you said x1 is what? 0. And
x1 is 0. Yes.
Okay. Oh, the least. Okay.
Yes, the least. This one is cost. That's why we shaded upwards. This one was greater than or equal to. This one is not less than or equal to. This one is not a maximization problem. This one is minimization problem. So we need, and the cost, we want the least one. Every rational entrepreneur would like to what? Incur the least cost. Every rational entrepreneur will what? Like to get or gain the maximum profit. So we are picking the least one. You get it? So
yeah.
This is talking about the minimum, right? So let's move on to the. So the answers. Yes. So this one they didn't bring the calculation here. So I've done it for you. So the B was 5 and 2. You get it? So I've done it for you. So for minimization problem, move the ISO. So the ISO with the profit ISO on something. I said I don't want to teach you that one because it might confuse you. Like, you get it? You might mix them with what I taught you. So I'm teaching you only one method. That's the graphic method. Then you pick the point, the corner point of the feasible region. Then you substitute it into the what? Objective function. Then you solve for it. If it is maximization question, you pick the highest value. That will be your answer. If it is a minimization question, you pick your what? Minimum. All right. So basically, this is what the linear programming is about. You get it? So we've done that of LP, maximize and what? Minimize. Thank you for your time. Next time you are going to solve LP using what? Microsoft Excel. You are going to use Excel to solve the thing within seconds. All right. Thank you.
Question.
Thank you.
A question.